Hello, welcome to Solar Dryer V1 with ProtoEarth.us. This is Jacob Claymeyer. We're going to be designing a solar soil dryer. And the base of this design is built off of a double pane window that was sourced for free through Facebook Marketplace. So you can filter for free on Facebook and find plenty of free things. But in particular, windows are actually very available and prevalent. So when I was looking for a window, I was looking for a double paned window specifically, and that would allow me to just convert it very easily to a solar energy collector. So what you're watching here is me taking measurements from the actual window and creating a representation of the window within Fusion 360. So just taking basic measurements with a metric measuring tape and putting it in here. You can see I'm using a rectangle tool, extrude tool to create the overall body. I sketch on that face and kind of just take some reference dimensions. So this is kind of the front of the window that you're seeing here. Now the plan is to paint the back panel or the back sheet of glass black with a flat black paint in order to absorb the solar energy, leaving the front window clear and having that back window be a nice black body absorber. We can use it as a solar energy collector. Now the inside of the window would then get hot from that. There's going to be some heat loss, of course, from the front panel and all the different sides that are made out of wood in this case. But overall, we're going to have an energy in from the sun. Here you can see I'm drawing the cutout for what was a latch. I just went ahead and unscrewed it from the window frame. And that's what I'm going to use as a way to get this heat energy out of the window. We could certainly cook things potentially within the window, but really what I want to do is get a convective flow of air to be moving throughout the window. And how that works is as the solar energy enters the window through the front pane, hits the back sheet of black glass, it'll heat that glass and heat the air in turn. And the air will then become lighter relative to the rest of the air in the atmosphere. So the way that kind of works is that the molecules of the air are more energetic and excited, so they want to spread out a little bit more, and that decreases the density of the air. So in relation to the atmospheric environment, they weigh less per fixed volume, so they're going to rise. Think of a balloon, right? That's filled with helium. Helium is a less dense gas than our normal atmospheric air. So it wants to rise. And where it's going to rise is out of these holes that we're creating. So we need to give it a place to essentially breathe. We're going to drill these holes. That's why I've shown them as circles. Now, this is the frame is built out of wood. So it might actually be really hard to drill these holes all next to each other, especially because this window is quite large and we don't have a drill press that would fit that size. So realistically, I'll probably just drill the two end sides or the two end holes and then use a jigsaw to cut between them. Now, I'm also creating holes on the bottom of the wood frame here. And that's because we need the flow to go from top to bottom. So, the heat has a place to escape, but the only way the air could enter if we didn't put these holes in would be from the top as well. So you wouldn't have a lot of good flow. You'd have some air going in, some air going out. So I really want the cold air to be sucked up from the bottom and then pushed out the top. And what that will do again is create that convective flow of warmer air that has the potential to dry the soil or whatever else we'll put in this box that we'll design after this window. As you heat air, its capacity to store water increases. And that's why as we heat it with the sun, it'll become a little bit drier, or it'll be able to soak up a little bit more moisture. So as we flow it over the soil, it will hopefully pick up some of the soil moisture and vent it to the atmosphere, and kind of moving more air through it is better than just baking it in a closed environment. We could make a solar oven, but the moisture wouldn't have anywhere to go, and the air would become quickly saturated, completely full of the water it can hold per its temperature. You can see I made holes on one side, and then I'm using the mirror tool now to create the same set of holes on the other side. That just saves me from creating the feature twice. Now we get to the fun part. We're going to create a drying box, and I'm going to design it to be 3D printed. I was working on a tight schedule. I was heading out to see the researcher that had requested this soil dryer. They're trying to take soil measurements of soil organic carbon in the field during their project this next summer. And this is a device we're prototyping to hopefully have some access for them. This bump out I'm adding is a sheet of expanded polystyrene with a reflective film. I added this to the back of the window to hopefully retain some of the heat that may have been dissipated off that back black sheet. So essentially I duct taped it on. It was material I already had around from another project. So went ahead and used that. Even I was able to cut multiple pieces and kind of puzzle piece it in as to not use a nice homogeneous or monolithic sheet of the insulation that might be better suited for another project. So yeah, this is actually where we get into designing this 3D printed top shell. And I created a new component to design it in. This is good practice in Fusion 360 to keep different bodies or things that you believe will be different components as different components, and that will allow you to join them, move them relative to one another, and do a variety of other things. It also helps with if you need to go back and modify one component, you can see that the design history down here at the bottom is simplified when you're only working in one component, so you know which features were associated with that component. The reason I'm starting in this location is because I know this is where the air is going to escape or move through the solar dryer. And I really want to interface with this in a positive way so that the piece that I design is always keyed in to this window frame. It's nice to have things removable, right, for iteration's sake, also for transport. So really, yeah, we're creating this air inlet first, deciding how it's going to key in. And then here I'm creating this circular shape that's going to be essentially the heating and drying chamber. It's circular because we need to be able to angle this solar dryer to the variety of angles that the sun can be at throughout the day. It moves, as I hope you know, in a big arc across the sky. And in order to get the maximum amount of energy input into this solar dryer, you're going to want to create or move the solar dryer to be perpendicular to the sun's rays so that it goes straight into that back black window pane and we absorb the maximum amount of energy. If it's off angle a little bit, that's all right. But more of the solar energy and rays will bounce off of the somewhat reflective first sheet of glass as well as the back sheet. No surface is 100% radiatively absorbent, except for maybe the vacuum of space gets pretty close. But we're just using high temp barbecue paint that I've got from another project. So we really do want to try to create a normal surface. And when we do tilt that window, we're not going to want the samples that we're storing within the hot chamber to potentially spill or be off axis. So by creating a circular chamber, we can have a variable flat essentially surface within it. So we'll create a tray piece coming up later in the video that gets inserted into this chamber. And it can also be rotated, right? As you rotate the solar dryer, it can change here. So now that we've got the basic chamber design from the end, we're just creating these little flanges that will come over the sides of the window. So we created that positive piece that goes into that middle section where the air is coming out. And now we're just creating two flanges to hopefully create a decent seal between the window and the, what should we call it? The solar box, the drying chamber. That's probably a good name. you can see how it kind of hugs the window on either side. And I referenced the window frame geometry. Later on, I think the first time I designed the window, I just took measurements with a ruler, but later on, I took measurements with a caliper and made sure I got the exact thickness of that window so that the 3D print would fit on there snugly. So it could be somewhat of a press fit, but also be removable without any sort of hardware. You saw I created a cap on one end. I wanted the air to flow up into this chamber and then out the right side where the user would interface with it. I'm keeping in mind how I'm going to 3D print it. You'll see when I enter in these wall dimensions, I use multipliers of 0.6 millimeters. And that's because my nozzle size on my 3D printer that I like to use is 0.6 millimeters. When you're designing for 3D printing, it's really important to understand overcuts and overhangs, but wall thickness is also very important, especially because I want this to be somewhat airtight, right? I want it to be able to hold in this air and this moisture until I want it to be released. So I'm really planning on printing it vertically, right? So that the circle is facing upwards as I 3D print it. So as I'm designing this, I'm keeping that in mind. And this is the part where I realize, the size of it right now is too large for my 3D printer. I've got a Creality CR10 V2. I think it has a 400 millimeter height that it can print, but I gave myself a little bit of margin in order to just make sure that it goes that high. This is actually the largest or tallest 3D print that I've ever made. But it ended up printing. We'll show those pictures later on. I always like adding fillets to my designs. You can see I go through here and pretty much all my design videos, you'll see fillets, and really it's about creating a better experience for the user. But there's a variety of other reasons. It can be a little bit stronger than a hard corner. So if it were to get hit with something, the stress would be distributed or flow through the object a little bit better. I like to think about stresses as really a flow of energy, and it's a flow of stress, right? As the molecules next to another molecule move, does it need to move sharply, or can it move gradually and distribute the load evenly? Here I'm removing some extra material that really isn't needed. You can see these chamfers will help just remove that corner. It's really not holding anything, but I do want a good grip on the window, so I'll leave the majority of the length. I think one way you could reduce material as well is put little holes across all of the side panels here. Now there's a variety of other materials we could have used for this chamber up top. There's plenty of other circular extrusions. So if you had a piece of PVC pipe, say, that was laying around that was the right size for you, we could have used that as the chamber and reduced the amount of plastic that we're printing here. But this will be printed in a recycled 3D printing filament, at least. It's not quite recycled where it came from other bottles. It comes from Coex LLC, where I get a lot of my other 3D printer plastic. Essentially, they have some waste and filament in their process, something that doesn't come out right. They're able to regrind it and extrude it into new filament, and it comes out this sort of odd green color that is probably a mixture of multiple colors that kind of went bad. So it's offered at a reduced price, and it helps them reduce the amount of waste that is removed. But ideally, we would be sourcing this plastic from some sort of circular economy, circular plastic chain, where different parts or prototypes like this could be discarded, ground up, and turned into new filament. the plastic does degrade over time if it's extruded and heated and cooled a bunch of times, but it's still better than having virgin plastic coming from a plastics and oil company essentially every time you want to create a new thing. This part shouldn't end up in the landfill. We should be able to recover it and at least try to use it for something else or reduce the amount of raw material usage in the future. And PLA itself, which is this material, does come from renewable sources. So I think it's mostly corn-based, and it ends up turning into hydrocarbons, and it's a very energy-intensive process. So it's not the most eco-friendly, but at the very least, we have no worries about running out of the material. And like I said, it has the potential for recycling, which is always good. So here you can see I'm changing the appearance of different things within Fusion 360. The white back represents the expanded polystyrene that I used as insulation on the back. You can see how there's a clear window pane and a black side as well. This just helps me as I design to really visualize it, make sure I'm considering it as a real thing, right? You want to get it right the first time. So as I'm designing, I really like this. And as I start to think about making the tray and the end cap for this heater, I want to try to design it in its intended state. So here we have the window and solar chamber or drying chamber angled at 45 degrees. And we'll create a new component and sketch off of the end face here to make that tray. Now within the protoearth.us post, we'll go over a couple different requirements for this tray. It's going to be used for scientific purposes, and a big part of the scientific process is removing extraneous variables. And we need to do so by allowing the user to clean the tray. And this is where I think I could have done better in this design. I think HDPE can be cleaned as a particular type of plastic, can be cleaned to lab grade standards. But what I wanted to do here is look at the potential shape that could fit within the solar dryer. For future use, you could vacuum form a sheet of HDPE to the shape that I would be designing here, and that would allow it to be cleanable. But for this prototype process, and as we're not sure how well this is going to serve as a dryer, I wouldn't go through that vacuum forming process for just a one-off. So I'll be 3D printing this tray out of the same material. You see that I offsetted it somewhat from center, and that will allow it to sit somewhat in the center, as well as not budge too much when it's in there. Here I'm extruding the general profile of the shape. You can see I offset it just to create, offset it from the interior surface of the circle just to create some manufacturing tolerance as I 3D print it. So as we go through and design little slots for the soil, I want to talk a little bit more about the use case for this solar dryer. In the research project, they're going to be measuring the amount of soil, the amount of carbon within the soil. And that's a gross oversimplification. But the important thing to know about this is that it's very important to soil geology to understand how much carbon is in the soil. I think it's a good metric of the amount of organic matter within it, as well as the amount of potentially saved carbon that is not in our atmosphere. And as we talk about the amount of carbon in our air, we have to talk about where it's coming from. It's not just coming from the exhaust pipes of our cars and our power plants and our planes. It's also coming from the soil, and the carbon in the soil has been built up over millennia as microbes and living things degrade and are in the soil. Even forest fires will burn the trees, and that soil will become more carbon rich from all that tree content. And when we till the lands and farm in ways that degrade the soil, that carbon becomes released and more available to be released into the atmosphere. So this research project is aimed at having a field deployable way to measure the amount of organic measure the amount of carbon within the soil without having to take it back to a lab. Really, as we talk about tracking our progress to a more carbon friendly and conscious world, we're going to need to make sure that this technology is available to everybody, not just the people that can afford the testing or that have a fancy enough machine to do so. It's an important metric for farmers to monitor their soil. It's an important metric for our world to measure our soils as well. Restoration type projects, even we talk about like a carbon market future where companies that potentially can't get rid of their carbon emissions could potentially buy offsets in order to at least fund a sector of the environmental economy that reduces the amount of carbon in the air. And this isn't, a carbon market isn't a full solution, but even if we wanted to employ it, there's issues with it because we really have trouble measuring the exact amount of carbon that is sequestered in many types of carbon sequestration, at least to like an accurate level. Of course, you can say that carbon was sequestered, but is it going to stay sequestered? How much truly is sequestered are points of contention, and you need a reliable and accurate way to do so to measure that retention if you're going to start selling these as potential offsets or framing them in that way. So if we were able to find a easy way using this spectroscopy method or another method that people could do easily and in the field, we could really start to track that better. Part of my design requirements as well for this was to take 25 50 milliliter samples. And I did some calculations in order to do so, but I think I maybe missed a decimal and ended up making 5 milliliter samples rather than 50. But I think the process still stands here where I create the profile of the shape that I'm interested in, and I'm able to select it and measure it to understand how much square millimeters would be in the area that I select. And then I'll extrude the amount of in the dimension to create that 50 milliliter, or in this case 5 milliliter divot. Also, creating these fillets on the inside is important as we think about trying to scoop out the dirt or clean it out. We don't want any sharp corners where things can kind of get situated or stuck. Because I sketched on the end face here, I need to offset where the extrusion starts. And after this, we'll go ahead and mirror this profile or this cut out of the board, and then we'll create a linear pattern in order to have as many of those as we can fit within this tray to maximize the amount of space and minimize the amount of plastic we're using. This tray ended up being quite strong. I think I could have used a little bit of a smaller fillet on a lot of these. Even filleting the insides, right? Rather than having just a straight extrude here, I could have gone back and created a more rounded bottom, but I was worried about my math being a little bit off, and worried about my math being off in the sense that if I created those fillets, that would fill up some of the space of my 50 milliliter, in this case again 5 milliliter sample volume. And the way we could have done it instead is to create this tray and then create the shape of the sample container as a positive shape, and made sure that that shape was 50 milliliters in volume, and then positioned it and subtracted it from the tray shape. And you can do that with two different bodies. You go into modify, subtract. But here we go. We're going to go ahead and mirror this profile to the other side and just use that same extrude tool that we used before. Now that we've got both sides extruded, we're going to create a linear pattern. We've measured the dimension from the inside wall to the outside, and now when we create that pattern, we select our feature, set the length to that value that we copied, and we're able to define how many of those we put in that space. I'm going to subtract the wall thickness that I would like on this end here. You can see the default is 3, but we can go in here and modify and increase the quantity until it looks approximately right. You know, you want to fill this with as many as you can. I'm getting a better angle at this just so I can get a little bit closer. And there's our tray of samples. To get dirt out of here, we could create a little tool to get in and out. But really, I think the design needs to be rethought. You know, it's kind of hard to get things out of there. This shape wouldn't be conducive to vacuum forming. You really want draft angles on vacuum forming so that the plastic can be released easily. But it does fit in there well, and it'll work well for this initial test window. I've skipped over a brief portion where we sized the tray appropriately, as well as the container. I think I shortened the length of the container or the solar container or dryer a little bit, just so it can fit a lid within it, and that the tray is all the way back against the fillet. So we're creating this lid now. I'm going to speed up this process by 2 times speed. You've seen all these tools before, right? We're projecting different geometry and we're using it to draw new ones, extruding that geometry that we draw and maybe taking chunks out that we don't need, and creating a physical object in that way. Now, what I'm thinking about in this cap here is I want it to potentially attach to this tray so that it can reduce the amount of airflow that happens below the tray. We want the drier air to be flowing over the soil samples in contact with the soil surface, not just heating it up. And when we were doing our tests, we came up with an interesting conclusion that, or an interesting thought that flowing air over the samples could be potentially detrimental to or affect the results of the test. And the reason for that is that, there's particles and different compounds within the air. So it might be better in the future to just heat the tray itself or to get the soil warm without having true air-to-air, air-to-soil interactions. But at the very least, we wouldn't have found that and we wouldn't have thought about that unless we completed this test in this prototype. So it's good to capture those learning methods. Now that we have the tray capped off, I'm going to need a handle as well as ports again to let the air out. And boom, there they are. Just adjusting the circles a little bit, had a little bit of fun creating an arrow and different shaped holes. And I'm just taking a look now, making sure that there's enough room for the air to get up above. And that's the window. I took this quick shot on my phone to show my friend, the researcher, how long it's going to print. Over a day to print this entire piece. It also has the amount of plastic we're using here. But overall, with the physical design in hand, we can feel confident that it'll meet our purposes, at least for this initial test. So checking in 18 hours and 56 minutes later, running the printer at quote-unquote 300% speed. Doesn't actually go that fast because it's limited by the acceleration rate. We have most of our parts almost printed. It's just working on this tray here, or the solar chamber. Again, we're printing in a 0.6 millimeter nozzle. You can see this is the filament runout sensor. That's the extruder. Again, that green plastic is the recycled plastic. Here's a closer look. Thanks so much for joining us in this design of a soil dryer powered by solar energy. More details on the project, including the base problem statement, the requirements, the life cycle analysis of this device, and more can be found in the link below. And I'm always open to questions, comments, positive remarks. So thanks for watching.